Okay, good morning. So we are meeting again to discuss our model 5 topics. Okay, right now. So in the previous class, we the topic was program type. So this we discussed. Okay, so in the program diagram, the idea is we have a CPU and we have IO interface model and we have devices. Okay, for example, here only one IO interface model is given, but there may be n number of IO models and n number of devices. Okay, so in the programmed IO interface, CPU has to so whenever CPU wants to have communication with any of the devices, it has to check the status bit of the corresponding devices in a corresponding IO model. Okay, and if that status bit is not ready, then it will go back and it will come back again after some time. So the responsibility is given to CPU, and due to that CPU, we are wasting the efficiency of CPU. CPU is meant for doing some complex operations, but we are asking it to do this status checking. So we are degrading its performance. So that's the problem with the programmed IO. But program IO still in use for low-end application because it's very simple to implement. It does not require complex hardware to implement. That's why we are using programmed IO even in nowadays for small applications like normal microprocessor, general 8085, 8086, 186 based applications, smaller applications we are using. But for complex applications, we cannot rely on programmed IO. So the next idea is interrupt driven IO. So this is the next concept. So interrupt driven IO. So interrupt driven IO is again a very simple mechanism. I mean, concept is simple, but implementation requires some special hardware and software programs. Okay. So here we have a CPU. Then we have IO models. So let me take again only one IO model. Then we have a devices, device 1, device 2, for example. Right. So now the idea is whenever CPU wants to talk to a particular device, whenever CPU wants to establish communication with a particular device in a particular IO model, what it will do, it will send that request. Okay, so CPU will send a request. That request will have which device it is going to talk out of these two, which device. So for example, device 1, I want to talk. I want to read the information from that device, something like that. So that type of request will go from CPU to the IO model. Then CPU will not bother whether during the time the device is ready or not. So its duty is it will just hand over this. I mean, it just request. Thereafter, it won't wait for the devices to become ready. So it can be engaged with some other work. So this is another program. Let us take another program. It is in the memory. So CPU is just running this program. Right. So whenever the devices are ready, either for example, in this case, device 1, right? Whenever device 1 is ready, it's a duty of IO model to check whether the device is ready or not. For that, it has some separate control signals to monitor the status of the device 1 and device 2. In this case, device 1. So it is just checking the device 1 status. Once the device 1 becomes ready, it is the responsibility of the IO model to intimate back to the CPU that the device 1 is ready. So that type of signal it will generate. who is generating IO model. Okay, so IO model generating that response because there was a request. Once the request comes, then only IO model will do that. Okay, and it will send a feedback for the request. Okay, right. See, CPU is doing some other work. While doing its work, the device may ready and the IO model can tell now the device is ready. If you want, you can talk like that. So from CPU point of view, since it is doing something, during that time it is getting some external signal. So from CPU point of view, this is called as interruption. Some interruption is coming because it is engaged with some other work. So it is getting some interruption, positive interruption actually to say, because it was requested, but now it is getting. But during the time CPU is not free, so it was doing something. So it is getting some interruption. That's why it's called interrupt-driven IO. Okay. Once the CPU gets some interruption like this, whatever the current instruction it is doing, it will complete. Suppose let us assume during executing this instruction of that particular program, it is getting interruption. Then it will complete this instruction. It will complete this instruction. Then it will store address of this instruction into memory. Then it will go to the particular IO device. Okay, so listen, I repeat again. Even some cases, CPU can even acknowledge, send an acknowledgement signal back for this. Some acknowledgement. So I just brief you again the steps. CPU wants to establish some interaction with D1, but device 1 is slow device, so it is a fast device. So most of the time the devices are not ready to whenever the CPU wants. So what happens? CPU will send a request. I want to talk to this particular device. Please do the needful like that. A signal will go to IO model. Then CPU will be engaged with some other work. Once a request comes, the IO model will keep on checking the devices. So whichever device the CPU sent the request, the device status will be checked by the IO model. Once the device is ready, the status will become active. During the time, the IO model will send one signal back to CPU. You requested D1, now D1 is ready, you can take care of it like that. But CPU was not ready. Able to see, Pop? Able to see what I'm discussing?
Yes,
Yeah.
sir.
So CPU was not ready. CPU is doing something, and whenever it gets some signal like this, it can send acknowledgement. Yes, fine. I will come like that. Then it will complete whatever it is doing, and it will keep pending. This work will be kept pending. The remaining part of the work will be kept pending. So it will complete the current instruction, whatever it is doing. It will store the starting of the pending. This is called pending part of the program, right? So starting point of the pending will be stored into the memory. Then it will get into the device 1, and device 1 related activities. It will complete. CPU will have interaction with the device 1. Once the device 1 related things are over, CPU will come back to the memory and it will start executing the pending thing. So this is what interrupt-driven IO. So the main advantage of this interrupt-driven IO, CPU is not kept idle. It is engaged with some other work till the devices are ready. Okay. And once the devices are ready, CPU will attend the device. Then it will go back to the original program. It will continue. So we are engaging the CPU effectively, and we are not forcing the CPU to check the status of the devices. So this is better compared to programmed IO in terms of efficiency. So please let me know whether the idea is clear. The interrupt concept is clear.
Yes, sir.
Thank you. Right. Now, there are few things we have to understand. Number one, though CPU has sent one request to the IO model and it is doing some work. Suppose this work is more important, high priority work compared to doing the device. Though it was, though the request already sent, but after that it is realizing this is much more important than talking to device one. In that case, it can also, CPU also can say negative acknowledgement. No, I don't want, though I requested, I don't want right now. I will check again. So like that, negative response also can go from CPU to the IO model, and CPU will continue doing this work and it will complete this work. Thereafter, again, it will send a request. So this is one way. Okay. So what I'm trying to say, whenever interrupt comes from the IO model, it doesn't mean CPU has to obey that. CPU sometimes can say no to that signal from the IO because the work what it is doing may be important than attending device one. Okay, so that is a possibility. Not always, but that way also we can make. Number one. Number two, if you want to have this type of interactions between IO model and CPU. So in the previous case, IO model is not doing anything. It's only CPU. CPU is doing all the things, right? Here, IO model should inform the CPU. So it is more, now the IO model has more responsibilities compared to the previous case, right? So it has more responsibilities, but that type of activity to do this IO model must come with some extra hardware mechanism. Okay, so these 2 points also we have to understand whenever we want to implement interrupt driven. So number one, negative acknowledgement is also possible. Number two, interrupt mechanism require some extra hardware to take care of sending the thing and monitoring whether acknowledgement has come or not. If negative acknowledgement has come, then what to do? If positive acknowledgement is coming, then what to do? So those type of intelligence, extra intelligence that IO model must have. Okay, so those can be taken care by some extra hardware apart from normal IO model. The IO model also comes with some extra mechanical hardware components to take care of all this. Okay, so interrupt driven IO, though it looks more efficient, but it is costly compared to programmed IO. So that's the reason why still programmed IO also in market or in use for low-end applications. Okay, so for high-end applications, we have to take care of, we have to implement interrupt-driven to get better efficiency. So this is a basic idea. With this idea, now let us get into the flowchart, slides. Let us understand. We discussed up to this. Yeah, in the previous class, I think I start at this point. Okay. Fine. So from a CPU point of view, what about the interrupt mechanism? So it issues the request to the IO model, and then it can do some other work. After completing every instruction in the some other work, it can check whether any signal has come from the IO model or not. In case if it's interrupted, it will save the current program and then it will attend the device. So from the device, it may fetch the data and store whatever operations. Okay, what it can do. So please try to understand this diagram, very, very important diagram. So what are the sequence of actions are taking place when interrupt is occurred? Okay, right. Now let us understand. So what is when interrupt occurs after instruction at location F. So it's a memory. It's the main memory. And there are registers in CPU. So it's a CPU. CPU. It's the main memory. Again, it's the main memory. CPU. Okay. Right. Now let us understand what are the sequence of actions are taking place when interrupt is occurred. Right. Fine. So first interrupt, first the device request signal will go from CPU to IO model. IO model is not shown here for the sake of simplicity. So a request from the processor will go to the IO model. Then what processor will do? It will work on some program. So let us assume. Excuse me, just hold on. Sorry. Okay. Usually I will put it in silent mode. I forgot. Anyway, right. So when it is executing this program during this time, it is getting interruption. So at this time, it is getting interruption. Please listen carefully. At this time, it is getting interruption. Okay. Right. Then this is nothing but address. N is n plus 1 are all addresses. Okay. So this is address of the next instruction. Address of the next instruction. So where we can find this address? This address is available in program counter. So we know program counter is a register which is holding address of the next instruction. Address of the next instruction to be executed. Is it or not? So while it is doing this program, during that time, interrupt is coming from the IO model. So this is the address of the next instruction. It is right now in the program counter. So this has to be preserved. Okay. And one more thing, up to this point, up to n, up to this n, some operations being done, right? So that results may be available in registers. It has some registers inside accumulator and other such registers inside the CPU. So they have to be preserved. Okay, right. Now, what will happen? There is a, I told you already in the memory, a portion of memory is reserved as stack. In the memory, a portion of the memory is reserved as a stack. Okay, right. The stack starting address, we should know. For example, the stack starting address is T. Okay, so the T will be accessed. The stack starting address will be accessed. Then from that address, the results. Right now, what are the results we have? That results are kept. Results means up to this. Up to n, there are 3 instructions, for example, here. Up to n, there are 3 instructions. The 3 instruction executed results are available in the registers, right? So they have to be stored in the stack. Okay, right. Clear. Next, this address n plus 1. What is n plus 1? CPU has to continue the remaining program once the interrupt is over. Okay, so it has to start executing from this point, right? N plus 1. So this n plus 1 data from the program counter is also stored into the stack. Right now, whatever the stack address t minus m, that t minus m will be stored into the stack pointer. T minus m will be stored into the stack pointer. Okay, right. Then program counter content will be modified from n plus 1. It will be modified to the device address. The device has some address, right? That device address will sit here in program counter. So CPU will get into that device. And it will, for example, the device related thing is available in the main memory. The device related operations are stored in the main memory from Y to Y plus L. So at Y plus L, the device related operation is over. At Y plus L, the device related operation is over. In that case, the N plus 1, which we stored previously, right? It will be popped back and it will be stored back into the program counter. The N plus 1 will be stored back into the program counter. What is in what is this N plus 1? N plus 1 is this address, right? Right. Then for the first three instructions, for example, some results are there now already we stored. They also stored back into the respective general purpose registers. The stack address again will become T because the stack is decremented after every retrieval. So the stack address will become T. Now again CPU will go to N plus 1 and it will start executing the program from this point onwards. This point is clear. Any doubt in this?
No, sir.
Okay, fine. So this is what the interactions happening between CPU, main memory, and IO model when the interrupt is occurred. It's a sequence of actions with respect to some diagram, some addresses. Okay, right. Now let me take one interesting case here. To answer me whether I don't mind whether it's right or wrong, you try to guess. Okay, suppose I'm writing a program just for example move r1 comma 08, move r2 comma 09, move r3 comma 06. So that's some program. So during the time interrupt is occurred. During the time interrupt is occurred. Now the sequence of actions I already elaborated, those things will take place. Okay, right. Now here we have some more instructions. Move R5, comma 05, something. Don't mind what I'm storing. I just want you to guess what will happen. Okay, so add a register, comma R5, something like that. Right. Fine. Now processor will get into the interrupt device and we have a program related to the device. The device is using same registers like this. Move R1, comma 07, move R2, comma 08, move R3, comma 09, and so on. Return. Whenever a return statement is given in the program, then it will come back to the main program. From this point, it will come back to the main program. Okay. Now, once it comes back to the main program, can you answer me what is the value of R1, R2, R3?
So 7, 8, 9.
7, 9.
Oh, that's the problem. What I told you. These results are
It's a
preserved.
temporary, right? So, sir, it will be 0, 8, 9.
Yes, because these are all preserved. Preserved in the sense what? These things are preserved. Okay, right? Now when it comes back, the R1 R2 will be get updated with same 0809, though the same R1 R2 are affected with are stored with different values. So what I'm trying to say, so this program, the results will be different, and this program, the results will be different. Okay, there are two independent programs. So this is program 1, program 2. So the results of R1, R2 here are results of R1, R2 of this program, program 1 and program 2 don't get altered. Okay, so that's what you have to understand. Now I'll go back to the same slide again. So just to look here. So here we have used R1, R2, for example. First instruction is R1, second instruction R2. And here we are, this is R1, let us assume this is R2. So we are storing the result, right? Fine. Now we are working out a new program. So in the new program, we have R1 with a different value, R2 with a different value. That value is stored in another part of the memory. And while retrieving, the R1, R2 will get the older value, not the value right now it has. That right now, whatever the value it is there, it is in the memory only. Okay. So same register we can use both in the main program as well as in the interrupt program. The values, whatever it is having, it is confined only to that program. The values are not taken to another part of the program. Are you all clear with this? So this many people having doubt. Okay, this is again a popular interview question. So what will happen if some registers are used in both the normal program and in the interrupt devices related program? So this is the answer. So they are limited with, or they are the data what they have, it is confined to that program alone. Okay, so the data will not taken to the program. So please try to understand this one. Fine. Now we have clear understanding of interrupt IO. Now what are the challenges we have? So in the example what I explained, I've used only one IO model and two devices. But in real scenario, there may be n number of IO models and n number of IO devices. So the first challenge is the processor should understand from which model the interrupt has come. In that particularly which device of that model the interrupt has come. So that the information should be known to the processor. Then only it can get into that particular device or particular model. Okay, that is point number 1. Point number 2. Suppose CPU initially has sent request to multiple IO models. In the assumption, at least anyone, whoever becomes ready, I just want to have communication. I want to talk to you all, but right now you are all not ready. Whoever comes, please let me know. Like that, it can send a request to all the IO models, and then it is doing some other work. Let us assume all the devices are becoming ready at the same instant. Then all the IO models will send a request, will send a signal to the CPU at the same time. Initially, no one is ready. Now all are ready. In that case, CPU should find a way to, CPU can interact only one device at a time. Okay, so now CPU should handle that issue. Okay, so for that, what they are doing, CPU is there, IO model is there, devices are there. Okay, let it be. There are IO models, and there are devices. Now, between we may use one interrupt controller or interrupt handler like 8259. there is one IC. It is called as interrupt handler IC. So CPU will send the request to the A2 finite. I want to talk to device 1. I'm ready to talk to device 2. Whoever ready, they can approach. I want to talk to device 3, like that, and send. This device will forward according to the IO model. So device 1 is available here. Device 2 is also available here. Device 3 is available here. So like that, it will distribute. And whenever the IO models are finding their respective devices are ready, they can send a signal. Yes, device 1 is ready. Device 3 is ready. Some information will come. Now this fellow will filter out among all the responses from the IO models, from all the IO models. It will filter out which one is more important among these. Only that will be forwarded to the CPU. Please go and attend device 3. So device 1, device 3, both are available, but device 3 is much more important. So please go on. Then CPU will not have any issue to go to device 3. Okay. So this A2 finite is called as interrupt handler. Interrupt handler, priority interrupt handler. In recent, in modern day system, the IO model itself will have this kind of handling mechanism. Okay. So the interrupt handler may be part of the IO model or external. If IO models are more, then external interrupt handler is needed. If IO models are minimum, but there are number of devices connected per IO model is more, then we will have interrupt handling mechanism here itself. So please try to understand the differences. There are two scenarios. Scenario 1. We have one CPU, always one CPU. We have IO models. We have number of IO models. And we have one device is connected per IO model. In that case, we need that interrupt handler here outside. Point is clear. Many IO models and simple devices are connected per IO model, 1 or 2. In that case, we need external IO handler. Okay, right. Area 2. We have CPU. Okay. We have CPU. We have IO model. Per IO model, we have multiple devices. Device 1, device 2, device 3. Again, one more IO model. We have device 4, device 5, device 6. Clear? So look at the difference. So here, per IO model, we have multiple devices. Here, multiple IOs, but single device. Okay. Now, the intelligence, the interrupt handling intelligence may be part of this IO model itself. Because if all the devices are ready here, it can set. Okay. Clear. In this case, again, one more challenge. The challenge is one line is coming from each IO model. If both IO models are saying, I have one device ready, I have one device ready, then we should have one more interrupt mechanism outside. Like that, the system complexity grows. Point is clear. Okay, so I think I can stop at this point because too many concepts I don't want to dump. Let me go slowly so that I want you to understand the concepts clearly. Okay, so what we discussed so far, the sequence of actions taking place when interrupt is occurred. When interrupt occurred, what are the sequence of actions are taking place that we discussed. And in that, the conclusion is the values are confined to a particular program. Values are not carry forward to the other part of the program in the interrupt mechanism. It is confined to a particular program. Interrupt program will have separate value. Main program will have separate value. That is number one thing. Number two, if multiple devices are approaching CPU at a time, how it can be resolved? It can be resolved with the interrupt handling mechanism, priority interrupt handling mechanism. A separate IC we have 8259. That interrupt handler IC will take care of that. But nowadays, IO models have inbuilt interrupt handling mechanism, and they can take care of their among their connected devices. But again, one more challenge: if every model will have one device ready at a time, then they can approach the CPU through exclusive IO lines, or they can be again given to one more external IO interrupt handling mechanism. From that, CPU can take only one. So by these ways, the interrupt mechanism is implemented. And since interrupt mechanism requires these type of hardwares, interrupt is only preferable for high-end applications, not for all the applications. In programmed IO, we don't have all this, right? We need IO model, but it is a duty of CPU. It will just check and it will interact. But here, though the efficiency is more, but it comes at the cost of extra hardware and extra amount we have to spend on implementing interrupt-driven IO. Okay, so I think I can stop at this point. We'll continue few more discussion on interrupt and DMO in the next class. Okay, right. So before I wind up this, I would like to remind you. So this Sunday you have to submit your assignment DA1. So those who have not done, make it fast. I mean, try to complete and submit. That is number one. Number two,